All right, welcome to section 3.5. In this section, we're going to talk about some real life applications of exponential and logarithmic models. And these are some of the more common mathematical models that are used in real life applications by scientists and doctors and things like that. So, most likely, depending on what you're going to be studying in college, most likely you'll see probably one of these three types of exponential or logarithmic models pop up in your studies later on. Okay, so I don't want you to think that all this stuff that we've been learning about exponential and logarithmic equations and functions is all for nothing. There is a point to it, and it will help you later on in your academic career. Okay, so we're going to talk about three main models: the exponential growth, exponential decay, and logistic growth models. And I'm just going to give you a basic form for each of those models, and you'll see them pop up. And a lot of the questions and exercises that we are going to be doing, in most cases, the actual model is given to you in the problem. So you don't have to create your own model. Maybe perhaps later on in your college careers, you will have to assemble your own mathematical model, but for the purposes of this section, in most cases, you will not. Okay, so let's talk about an exponential growth model first. An exponential growth model, you're going to notice that when I write this on the board, it's going to look very familiar to something that you have already seen before. So it looks something like this. We have y equals a times e to the bx, right? And that should look very, very familiar to our compound interest formula that we derived at the beginning of this unit. It should look a lot like a equals p times e to the rt. So it looks like compound interest formulas, right? It looks like compound interest. And it should, because any compound interest model is an exponential growth model. When we talk about compound interest, you have money that's growing exponentially. So it's an example of exponential growth. The next one is exponential decay, and it's going to look exactly like the exponential growth model, except the only difference is this parameter b in the exponent is negative. So we have y equals a times e to the negative bx, and that negative turns it from an exponential growth model to an exponential decay model. Okay, and then the last one down here is known as a logistic growth model, and it looks a little scary when you first see it, but it looks something like this. It's y equals, and then you'll have a parameter here in the numerator called a, just a number of some kind, over 1 plus b times e to the negative r x. I know that looks kind of scary, but we're going to do an example with that, and it's really not so bad. But logistic growth is used to analyze population growth or the spread of viruses in situations where at first you have a big booming growing population, and then at a certain point it starts to taper off and slow down. So this happens a lot with perhaps a new species is introduced to an environment, and at first they grow, and then after they demolish their food supply, their population growth tapers off and sometimes stops growing altogether. Spread of viruses and contagions is another one that logistic growth models are used for. Okay, so we're going to go ahead and take a look at our first example here, and this is an example of exponential growth. In a research experiment with fruit flies. Okay, so a population of fruit flies is increasing according to the law of exponential growth. Okay, so that's kind of important. Once they tell us that we're dealing with exponential growth, we know that we're going to be dealing with the exponential growth model. Y equals a times e to the bx. Okay, and then they tell us that after 2 days there are 125 flies, and after 4 days there are 350 flies. What they want to know is they want to know how many flies there will be after 6 days. And this is a common practice with scientists, is sometimes we don't have 6 days to conduct an experiment. Maybe we only have 4 days, and whatever information we gather in that 4 days of research, we have to use that to make predictions about what would happen if we continued this on for a longer period of time. So, and to make those predictions, you have to have a good understanding of mathematics. Okay, so what we're going to do here is we're going to let y equal the number of fruit flies after x days. Okay, so x represents the number of days, y is going to represent the number of fruit flies after so many days of them populating. Okay, so here's what we know. We have two pieces of information. They tell us that after 2 days, so let's say when y equals 125, x equals 2, and when y equals 350, x equals 4, right? And that comes from this particular sentence right here in the problem, right? They give us those two pieces of information. What we're trying to find is how many flies there will be after 6 days. Now, this is going to be a very complicated problem. So if you get stuck at any point during this problem, hit the pause button and go back and watch it again. Okay, don't try and continue on through the problem. If you missed a step or something like that, make sure you pause, go back, take advantage of the fact that this is a video lecture. Okay, so use that technology to your advantage. All right, so here we go. Here's what I have. Based on these two pieces of information, I have two equations. 125, right, is y equals a times e to the b times 2. Right, so all I did was I took these two pieces of information and I plugged it in, one for y, and then I took this 2 and I plugged it in for x. And upon analysis, I see that the two things that I'm missing are my two parameters a and b, and I need to find out what those parameters are. So then to do that, I'm going to need to make use of both pieces of information. So I'm going to do the same thing with the 350 and the 4. So another equation that I have is 350 equals a times e to the b times 4. Right, so I have two equations. And two unknowns. So this would suggest that I should use a system of equations, right? So use a system. Right? And if you know how to use a system of equations, you know that you can use substitution or the substitution method to solve for these two unknown variables. And that's exactly what I'm going to do here. So I'm going to pick one of these equations and I'm going to isolate one of the parameters. So over here in the first equation, 125 equals a times e raised to the 2b. I'm going to go ahead and get a all by itself by dividing by e to the b times 2 on both sides. Okay, so now I know that 125 over e to the b times 2 is equal to a. And if I know that, if this is what a is, then I can take this expression, which is a, and bring it over here to my second equation and drop it wherever I see an a. So now what I have in my second equation is 350 equals, and instead of writing a, I'm going to substitute in that expression. I'm going to have 125 divided by e to the 2b times e to the 4b. Right, so this a became this right here. And now what I have, by making that substitution, I have an equation in terms of one variable, b, and I can solve for that variable b. Okay, so I'm going to rewrite this. I'm just going to clean it up just a little bit here. So I have 350 equals 125 e to the 4b over e to the 2b. And all I did was I cleaned it up a little bit and I multiplied in the top, and it didn't really change a whole lot, but it makes it easier to see this little piece of the equation right here. And I'm just going to bring that off to the side. So e to the 4b over e to the 2b is two exponentials with the same base, so I can apply properties of exponents here, and I know that this is going to be equal to e to the 4b minus 2b, right, which is e to the 2b. So that part of the equation that I have outlined in red here, I can rewrite, and my equation now looks a little bit like this. So 125e to the 2b. So that's a lot nicer, and I'm well on my way to being able to solve for b here. So I'm going to go ahead and divide by 125 on both sides since I'm trying to isolate the exponential part of this equation. And what I end up with here is 2.8 on the left-hand side. So 2.8 equals e to the 2b. And then using what I know about solving exponential equations, I know that I can take the natural log of both sides here. So I'm going to kind of continue this over here. So I have the natural log of 2.8 equals the natural log of e to the 2b. And then I can use the product or the power property to bring the 2b down to the front of this natural log. Okay, so now I have the natural log of 2.8 equals 2 times b times the natural log of e. And you should recognize that the natural log of e equals 1. So now what I have is the natural log of 2.8 equals simply 2b. And then I'm going to divide both sides by 2. Right, to get b by itself. So what we find is that b is equal to the natural log of 2.8 divided by 2. And I'm going to bring up my calculator here, and I'm going to go ahead and calculate that number. So the natural log of 2.8 divided by 2, and I get 0.515, let's say, 0.515. We'll round to 3 decimal places. So 0.515 equals b. Well, now that I know what b is, I can take that b and I can substitute it back in to find a, right? So I'm going to come back over here. So if you don't know what I'm talking about this guy right here, 125 over e raised to the 2b, right? And now that I know what b is, I can plug that in and find out what a is going to be. Okay, so I have a equals, I'm just going to say a equals 125 over e raised to the 0.515, a little dot right there, times 2. Okay, and to do that calculation again, I'm going to bring up my calculator, and we can do that real quick. Oh, geez, this thing, I tell you. There we go. Okay, so we have 125 divided by the e, second natural log, right? Hit second natural log to get your e. Then I'm going to have 0.515 times 2. And then I'm going to close parentheses. Got to delete that. You can have the exponent and close parentheses and hit enter. And I get 44.63. Okay, so we're going to say a equals 44.63. And you're like, what are we doing right now? What is it that we're trying to do? What we just found were the parameters of our logistic, or not our logistic, but of our exponential growth model. We found A and we found B. So now we can actually construct a viable growth model and start making a prediction about the future. Okay, so we have our parameters. That's what we solve for. We solve for A and we solve for B. Okay, so I'm coming back up here. So we started here, right? We started with this. And we're going to go ahead and substitute in our parameters and see what happens. So I'm just going to clear some room here. And I know now that we have y equals, I know that A is 44.63 times E, and I know that B is 0.515. So all I did was I took that A and that B that I found using a system of equations and plugged it back into my original growth model. So now the only unknown is X. Right? So if I want to know how many fruit flies there are after 6 days, I just have to take 6, right? I'm going to take 6 and plug it into X and do a simple calculation. Okay, so y equals 44.63 times e to the 0.515 times 6. Okay, and what we find when we perform that calculation is that it is a population of 980 fruit flies, approximately. I'm going to round to 980 fruit flies after 6 days. Okay, so this is kind of where I found my answer here. I know it's kind of hard to see with everything that we have already done. So, like I said, if you got confused at any point during that problem, make sure you rewind, go back, and just follow real closely and watch it as many times as you need to make sense of it. If you still have questions, make sure you come and see me during study hall. Okay, our next problem deals with exponential decay. And in our exponential decay problem, they actually give us the model that we're going to be using. You see, in the last problem, we had to build our own model. And that's a difficult process to do sometimes. But this is a much nicer problem because they give us the model that we're going to be using right here. Okay, so a carbon dating model is given. And the formula denotes the ratio of carbon 14 to carbon 12. So pretty much everything in the world has some composition of carbon 14 and carbon 12 present at any time. All right. So in organic material, the amount of carbon 12 stays the same, whereas carbon 14 is radioactive and it begins to decay with a half-life of 5,700 years. Okay, so once something has lived and it begins to decay, the carbon 14 begins to dissipate, and we can use how much of that carbon 14 is missing to determine how old something is. So it's a really neat process, and it uses math that you are now familiar with. And this is some of the math that archaeologists use, geologists, and scientists of that nature that have a lot of their field depends on determining how old something is. So carbon dating is a big thing. Okay, so let's go ahead and do this. So it tells us that we have a model R equals 1 over 10 raised to the 12th power times E raised to the negative t over 8223, right? And then they actually do an analysis of whatever substance it is that they are analyzing, and they find that R is this right here, 1 over 10 to the 13th power. So we can take that 1 over 10 to the 13th and plug it right in where we see R. Okay, so now I have 1 over 10 to the 13th power equals 1 over 10 to the 12th power times e to the negative t over 8223. And we want to know how old it is, right? So the part of this equation that we're trying to solve for is this guy right here, t, right? So we're trying to get t all by itself and figure out how old this fossil is. Okay, so the first thing I'm going to do here is to start to isolate that exponential portion of the equation. So I'm going to divide both sides by 1 over 10 to the 12th. And when I do that, on the left-hand side over here, what I'm left with is 1 over 10 to the first power. So we just get 1 over 10. And on the right-hand side, we're left with e to the negative t over 8223. Okay, so again, we can use one of those strategies that we talked about in section 3.4. We can take the natural log of both sides of this equation and then use the power property to pull that exponent down. Okay, so we have the natural log of 1 over 10 equals the natural log of e raised to the negative t over 8223. Oops, need a bigger parentheses. Okay. Then using the power property, I can take this exponent and I can pull it out front of the natural log. Okay, so what I have now is the natural log of 1/10 equals negative t times 8, or divided by 8223 times the natural log of e. And we've seen this so many times, but you should know, God, I hope you know that the natural log of e is 1. Okay, so we're just left with the natural log of 1 over 10 equals negative t over 8,223, and the natural log of e just kind of drops out because it's simply 1. Okay, so to continue getting t by itself, I'm going to multiply both sides by 8,223 on both sides, and they'll cancel on the right, and we get 8,223 times the natural log of 1/10 on the left equals negative t. And I don't want negative t, I want positive t, so I can multiply both sides by negative 1, and I get positive t on the right and a negative over here on the left. So there's my calculation. So once I plug that into the calculator, I'm going to know exactly how old this fossil is. So that's pretty cool. So I'm going to drag this over here, and let's do this calculation. Okay, so I have negative 8,223 times the natural log of 1 divided by 10, and I'm going to hit enter, and we get 18,934, right? So t equals 18,934.16 years, right? Because t is in years. So there you go. That's how old the fossil is, using some of the mathematics involved in carbon dating. Okay, very cool problem. All right, let's do one more here, and this is an example of logistic growth. Okay, so this is the sorry, this is the analysis of a growth of populations that initially have rapid growth followed by a declining growth rate. Okay, so something that starts off real fast and then tapers off. So a model for this type of population is what's called the logistic curve, and we're going to be taking a look at a college campus that has a population of 7,500 students. And one student returns from vacation with with a contagious, long-lasting virus. So he goes somewhere, he picks something up, and he brings it back with him to the college campus. And the spread of the virus can be modeled by this model right here. So they were nice, and they've already given us the model. We did not have to construct the model ourselves. And they're telling us that y is the total number. So this is kind of important, right? So y is the total number of infected students, and t is the length of time in days. Okay, and then they also tell us that the college will cancel classes when 30% or more of the entire the entire campus population is infected. So once 30% of our 7,500 students are infected, they're going to cancel classes to prevent further spread. Okay, uh, so the first question that they're asking us here is how many students will be infected after 4 days. So they instantly give us a key piece of information right there. They tell us that t equals 4. Okay. And we want to know how many students are infected. Well, that's y, right? We said y represents the number of infected students, so y is what we're trying to solve for. And if I look at that logistic growth model that they gave us, there's only two unknowns. There's either y or there is t. Okay, so in this case, we're solving for y. So we have y equals 7,500 divided by 1 plus 7,499 times e to the negative 0.9 t. And instead of t, we're going to go ahead and put in 4, right? Because we want to know how many people are infected after 4 days. So I'm going to multiply that by 4. Very good. All right, so let's go ahead and continue here. All we have to do at this point is start calculating stuff in our calculator. It's already solved for. We don't have to move anything around. It's just a matter of simplifying and doing the calculations. So I'm going to pull up my calculator here, and I'm just going to start with that bottom piece. So I'm going to start by calculating what is e to the negative 0.9 times 4, right? So second ln here, so I have negative 0.9 times 4, right? So I'm going to hit enter, And that's 0.027. So when you have some of these complicated expressions like this, sometimes it's better to tackle it one piece at a time. And just remember that if you do chop it up like this and you round your decimals, your rounding could cause your answer to fluctuate compared to everybody else's depending on how they round it. Okay, so your answer might not be 100% exactly the same as mine. Okay, so we're going to have 7,500 over 1 plus 7,499 times, and then we had 0.027, let's say. So 0.027. Okay, and then I'm going to bring my calculator back up and I'm going to go ahead and finish off the bottom, get a good clean number for the bottom. So I have 1 plus 7,499 times 0.027. And I'm going to hit enter. And what we get in the denominator of our fraction here is 203.473. So I have 7,500 divided by 203.473. And then we can go ahead and do that calculation. So we have 7,500 divided by 203.473. And what we get is 36.85 or 35 or 36.86, if you will. So 36.86 students are infected after 4 days. Okay. All right. So let's move on. Part B here. So we were able to answer that one. Part B, a little bit more difficult because what they're asking for is how long is it going to take if this were to continue to grow, how long would it take before the college started canceling classes, right? So if you recall, the college said that they were going to cancel classes after 30%, right? So I'm going to go ahead and write that down. So at 30%, classes are canceled. Okay, so what we really need to know here is what is 30% of the population. So if you recall, we had 7,500 students on campus, and to find 30%, I just multiply by 0.3, and we find out that that is 2,250, right? So 2,250 students represents 30%. So now the question is, how long is it going to take to infect 2,250 students? Question mark. Okay. Well, so 2,250 infected students, right? So this part of our problem, this 2,250, represents y, right? Because y represents the number of infected students. So we want to know how long it's going to take to get to that number. So I'm going to go ahead and use my logistic growth model. So I have 2,250 equals, and then I have 7,500 in the numerator. Actually, I'm going to move this over because we're going to need some room. So we have 2,250 equals 7,500 over 1 plus 7,499 times e to the negative 0.9t, right? So this one's different from the first one in that we're not solving for y anymore. We're trying to solve for t, which is buried in this complicated expression that we have. But not to worry, we have all the tools that we need to be able to get t all by itself and find out how long this is going to take. Okay, so I'm going to go ahead and scroll up a little bit and we'll start the process of solving this equation for t. So notice that the first thing I would like to do is get rid of that fraction. I don't like the fraction, so notice that what I can do here is I can put a set of parentheses around this entire expression in the bottom. And if I treat that as some number, who cares what it is, it's just a number, I can multiply both sides of my equation by that number or by that expression. Okay, so I'm going to multiply both sides here by 1 plus 7499 times e to the negative 0.9 t. And I'm going to do that on the other side as well. Right? Oops. There we go. So when I multiply both sides of the equation by that expression itself, the expressions cancel over here on the right-hand side, and what I'm left with is 1 plus 7499 e to the negative 0.9 t times 2,250 equals 7,500. And voila, I no longer have a fraction or a nasty looking fraction that I have to deal with. I do want to start getting t by itself. T's over here on the left-hand side, so I'm going to start moving everything away from the exponential part of this equation that I can. So I'm going to go ahead and divide both sides by 2,250. And what I end up with is 1 plus 7499 times e to negative 0.9 t equals, and what I get over there on the right-hand side is 3.33. Okay, so it's a 3 and a third. Okay, I can subtract 1 from both sides, and I have 7499 e to the negative 0.9 t equals 2.33. And then I can divide both sides by 7499. Okay, give me some more room to work here. These problems are long. Okay, so the 7499s, they cancel out. So I get e to the negative 0.9 t equals, and then over here on the right hand side I get 0.000311. You can verify that in your calculator if you wish. And then I'm right back at this stage now. I have the exponential isolated over here on the left hand side. I can go ahead and take the natural log of both sides. So the natural log of e to the negative 0.9 t equals the natural log of 0.000311. And now I can go ahead and use the power property to pull this negative 0.9 t out front here. Okay, so I have negative 0.9 t equals, well, hold on a minute. I don't want to gloss over anything here. We still have a natural log to the e, but you should recognize that that is 1. It will drop out. Equals the natural log of 0.000311. Okay, so the natural log of e is 1. Right, so box that, that's 1, so it's just going to drop out, and I have negative 0.9 t equals the natural log of 0.000311. And then one last step here to get t all by itself is to divide by negative 0.9 on both sides of the equation. Okay, so those will cancel, and we find that t is going to be equal to the natural log of 0.000311 over negative 0.9. And we'll go ahead and pull up the calculator here and figure out what that is. Okay, so we have the natural log of 0.00031 divided by negative 0.9. And we'll go ahead and hit enter, and we get 8.97, right? So t equals 8.97 days. So to answer our question, I'm going to scroll back up here. To answer our question, how long will it take to infect 2,250 students? It will take approximately 9 days to cancel classes. It's pretty quick. 9 days, 30% of your college campus could be infected by some virus. Okay, that concludes notes for 3.5. We are going to practice more of these problems in class together. These are difficult problems. They require a lot of practice. And if you need additional assistance, make sure you come and see me during study hall. Thank you very much.